So everyone knows me. I'm Ali Kashani, and I'm presenting my PhD research on data-driven constraint control here in the presence of my advisor, Dr. Danielson, and my other council members, Dr. Wang from the Mechanical Engineering Department, Dr. Peter, and Dr. Rishi from the Agriculture Department of the University of New Mexico. So before jumping into the technical stuff, let me talk about myself a little bit. I have a bachelor and a master in electrical engineering. During my master at the University of Tehran, I worked on this model reference adaptive controller for controlling a nonlinear delta robot in a laboratory size. And as you can see, we came up with a model identifier that had the fastest convergence rate. And we can see it can give us a really good tracking performance. When I started my PhD at UNM in 2021, I started working with Dr. Danielson on an external seeking control problem. The figure on the top, you can see it's a drone seeking for the source of a gas leak. And in the external seeking control problem, there's a non-cost function that need to be optimized. And as you can see, as the drone moves on its trajectory, it gets an estimate of the gradient of the cost and moves toward the maximum concentration, which is the source of the gas leak. Then with Dr. Shirin Panahi, who is now a professor at Oregon State, we worked on larger scale model predictive control, and we used group theory to reduce the computational complexity by a factor of 10. Then I started working with a team of researchers from Duke University on computing invariances from data. We published some papers on Automatica and LCSS, control system letters, and some conference papers in American Control Conference and IPAC and NeurIPS. So let me give you an outline of what we are going to study today. First, we're going to look at safety critical systems, which have some hard constraints that cannot be violated. Then we formulate the problem and see how invariance can help us to solve this problem and guarantee recursive feasibility. And then we will look into computing invariances from data and the sort of guarantees we can give for the data-driven approximation. And then we will compute control invariances using the algorithms that we developed, and then design a switch controller using these control invariances. These are two of the problems we worked on. The top is a soft landing problem when the system should stop right at the equilibrium and it should not violate the equilibrium. It should not pass over the equilibrium. So the position cannot be negative. The second one is a lane keeping problem where there's a trajectory that the car is traveling and we want to modify the controller such that the car doesn't go off the road. And so these are safety enforcing controllers that we are going to design. There are many other applications that we can apply our method for. For example, in smart grids, a short circuit fault or an open circuit current, open circuit voltage may cause a surge and cause fire. 90% of wildfires in California are due to power lines. And if we design a constraint enforcing controller using inverters, because circuit breakers are slow, we can prevent this power surge. In robotic systems, for example, in robotic assisted surgery, there are some limits on the robot. That there are some force limits and position limits that should be respected, and even we can have constraint enforcing controllers that even the surgeon makes a mistake, it prevents damaging an unintended tissue. In industrial robot, there are some obstacles in the environment. There might be a misplaced object, there might be a human walking in the workplace, and this constraint should be enforced deterministically. There's also another interesting problem where there are devices to regulate the glucose level of diabetes people, and people approach this problem by just regulating to a certain level, while the human body may show underdamped behavior in that level, and it might violate some safety levels. The glucose level might violate some safety levels. But if we approach the problem as a safety enforcing controller, we can keep the glucose level in certain intervals. Now let's about the problem. How we can formulate this problem. There is a loss that needs to be minimized, for example, tracking error or fuel consumption, and the system has some dynamics. The system follows some dynamics. The current state can be measured, and there are some safety concerns that need to be addressed, and we might also have limited authority over the input. So the first question that we need to ask is this problem initially feasible for this initial condition that we are at? For example, on the right you can see a trajectory that the blue trajectory travels safely, but the red trajectory is an obstacle. Solving that infinite horizon planning is not possible numerically, so instead we solve a finite horizon planning, and now it raises another question that does enforcing constraint in finite horizon guarantee constant satisfaction for the those times outside this planning window? Or we can pose this question another way: is the problem recursively feasible if we do a receding horizon planning, where the input is computed, the first input is applied, and then at the next iteration we compute the input again? The answer to these questions is that the system is initially feasible, and it will be recursively feasible if we start from an invariant set, and the inputs that we compute keep the state inside the invariant set. And it has an if and only if relation. This problem becomes even harder when the dynamics are unmodeled, and we want to use data to compute invariant sets to provide that recursive feasibility. The data we use are in the form of state pairs. And this is state pairs. It means that we choose some states, apply to the system for one step, and then collect the successor state. It can come from a gridded state space in the constraint set, or some random states, pick some random state applied to the system, or it can come from some trajectories. We look at two successive states and create our data set. If the state is not accessible, under some mild assumption, we can use state trajectories. We can use output trajectories to create state, to create some notion of state. So if the measurement is difference flat, we can create a window of measurement and treat them as the state of the system. We also need to know an upper bound on the system, on the order of the system. Now, how can we? Let's talk about invariance and what do we mean by invariance. We define a positive invariance set as a set of states that if the system starts from those states, it remains in the set for all time. And we define control invariance set. It has a similar definition But a control invariant set is a set that if you start inside the set, there is a sequence of inputs that keeps the trajectory inside that set. There are some geometric conditions that can be used to verify invariance. If the dynamics is described by this function f, the predecessor of a set is defined as the pre-image of the set, which means that the predecessor of the set X is the set of states that map to the set X. The successor of the set X is a set of states that map from the set X. And the geometric condition tells us that a set is positively invariant if it lies within its predecessor and its successor lies within it. There are some standard methods that use these geometric conditions to verify and create invariant sets. These algorithms work like this. It starts with the constraint set. So the candidate invariant set is equal to constraint set. And then it computes the predecessor set. Then it intersects the predecessor set with the invariant set and repeats this process until the candidate invariant set is a subset of the predecessor set. It means that the algorithm has converged. This algorithm, these standard algorithms can be applied for linear systems with polytopic constraints. You can see on the right, there's a linear system with polytopic constraints and how the algorithm converges. But for nonlinear systems, they are tricky because computing the predecessor set is hard for nonlinear system. It might need solving a non-convex optimization. And when the dynamics are unknown, this algorithm becomes even harder, and my colleague Amy at Duke University is working on those algorithms. So instead of geometric conditions, we can use functional conditions to verify invariance. If we define an invariant set as a sublevel of a function b, then the invariance condition tells us if v at some state x is less than 1, then v at the successor of that state should also be less than 1. We can enforce this condition using Lyacomov stability. So if we enforce v of x plus should be less than v of x, then whenever v of x is less than 1, v of x plus would also be less than 1. On the right, you can see a damped pendulum and its invariant set. It starts inside the invariant set, admits to the Lyacomov condition, and remains inside the invariant set for a long time. But this condition does not describe many other systems that we can actually compute invariant sets for. For example, this is a Van der Pol oscillator that we computed an invariant set for. And this system has a stable limit cycle, meaning that it is unstable in the region inside the limit cycle, and it is stable in the region outside the limit cycle. We can see two trajectories, one starting from very close to the origin, and the other from outside the limit cycle, and they converge to the limit cycle. So for these type of systems, we define a barrier condition that we came up with. It has a convex combination of v on the right-hand side, and this allows increase in the function v inside the region of the invariance. But invariance is not enough for safety. For example, the whole state space is an invariant set, because if you start in the state space, of course, we will stay in the state space. So we need to take into consideration the constraint set. If we define the constraint set using a unity sublevel of some function g, then if we enforce this condition that v is greater than g everywhere, then we will have the admissibility condition, which is the invariant set should be a subset of the constraint set. So if the invariant set is a subset of the constraint set, Because trajectories stay inside the invariant set, they will also stay inside the constraint set. We slightly relaxed this condition during our research and realized that if this condition holds outside the constraint set, that would be enough. So whenever G is greater than 1, B is also greater than 1. But here's a question, is this function G always given? How can we design it? There are some methods. The simplest one is to create an indicator function that is 0 inside the constraint set and is 1 outside. It's greater than 1 outside the constraint set. You can see the unity solvable gives us the constraints. Another method another method is using Minkowski functions that will give us a Lipschitz continuous function G, and this is useful for giving the deterministic guarantees. For deterministic guarantees, we will need this function G to be Lipschitz continuous. But the indicator function is not even continuous. So under some assumptions, if the constraint set is compact, convex, and contains the origin, we can create a Minkowski function. A Minkowski function, it returns on a set. It returns the minimum inflation required for that set, such that it contains a point. So if the set, for example, is a ball, and the point is outside this set, this ball should be inflated until it contains the point. So this value of rho would be greater than 1. And if the point is inside the set, then it could be deflated until it contains the point, and the value of rho would be less than 1. And it gives us sort of the notion of a distance with respect to the shape of the set. So what if those conditions do not satisfy, especially convexity? In many applications, the constraint is not convex. So we came up with a data-driven approach that will start with the indicator function. Indicator function can be defined for any set. And then, although we may not be able to create a continuous function for the constraint set, we create an inner approximation set of the constraint set. And then we create a Lipschitz continuous function for that set, using some Lipschitz continuous nonlinear functions phi and a linear combination of these nonlinear functions. And then we solve this optimization problem. We try to maximize the volume of the inner approximation with respect to this constraint that the inner approximation should be a subset of the constraints. Here is an example. In this example, inside the big box and outside the small box is the constraint set. It is non-convex. And we use this method to compute the constraint set, and then we compute an invariant set. You can see the trajectory is starting inside the invariant set, safely travels, but trajectory starting outside the invariant set collides with the obstacle. This can be used for applications like collision avoidance and reachable. Now, how can we actually compute these invariant sets? Our first approach is inspired by Lyapunov functions. Because it's well known that a sub-level of a Lyapunov function is an invariant set. A Lyapunov function should satisfy 3 conditions. It should be 0 on the equilibrium, it should be positive everywhere else, and it should satisfy a Lyapunov decrease condition. But previously we saw that this Lyapunov decrease is too conservative for computing invariant sets for locally unstable systems. So we replace this with the barrier condition that we developed. And then we create a neural network. This can have several hidden layers. In our work, we do not consider hidden layers, but in the literature, people use a multi-layer neural network to create invariant sets. The first condition is enforced by subtracting the bias from the activation functions in the last layer. And the positive definiteness is enforced by having a positive definite matrix P and taking the norm of the output. So these two conditions are enforced by design. This condition should be learned. In the literature, they put this condition, the deviation of this condition as the loss function, try to minimize it, but that does not provide guarantees. We're gonna give guarantees that this condition will hold. And I made the equilibrium red here because I will talk about it later. So we want to compute an invariant set O that respects the constraint set X. We want to minimize the function B because it rewards enlarging its sublevel O. And we want to enforce the invariance condition as well as constraint admissibility condition. We do that by solving this semi-definite program. The cost is minimizing a measure of V over the constraint set X, subject to this invariance condition for every state in the constraint set. And the constraint admissibility condition is enforced using this LMI. So whenever P is good, P minus CC transpose is positive definite, we can have constraint admissibility. Solving this problem is still infeasible because this is a semi-infinite STP, meaning that we have infinite constraints because that the invariance condition should hold for every state in the constraint set. If the system is linear, we can create an LMI and solve this, but when the system is non-linear, this becomes really hard to solve analytically, and when the model is not available, this becomes even harder. So we approach the problem using data-driven methods, where we use our data set and enforce this invariance condition only on data. This makes the STP with finite constraints that we can solve. And we also add a buffer. Why do we need this buffer? Because when we enforce a constraint on just data samples, we wouldn't know what would happen between the samples, in the gap between the samples. So if we add a buffer, and this buffer is related to the Lipschitz constant of the dynamics, the Lipschitz constant of activation functions, the data density, and then we can ensure that the solution to this problem gives us an invariance set for every state in the clusters. Still solving that semi-definite program, even with finite constraints, is hard. The solvers doesn't act rationally. It gives me errors, warnings. They give me infeasible solutions. So I decided to do a LP relaxation of this STP. And also there is also another problem that the number of parameters is quadratic with respect to the number of activations. But we can alleviate these issues by synthesizing P as CC transpose plus some linear combination of some positive definite matrices. This CC transpose already gives us the admissibility condition, and if we solve for positive values of alpha using this linear program, we can also have we can also create P, stack P back in B, and get an invariance. Now let's talk about the equilibrium. If the system is unmodeled, how do we know the equilibrium? If the system is symptotically stable, and we have long-term trajectories, then we can just sample the last point on this trajectories, take an average. It's a very intuitive approach. And if the system is symptotically stable, then we showed that there is if the system is asymptotically stable and the initial optimization problem is feasible with the actual equilibrium. We showed that there's a long enough trajectory that the optimization problem using the approximated equilibrium is also feasible. And you can see the approximation is very close to the equilibrium. So let's talk about results. Using this method, as you can see, we computed some invariances that they contain the equilibrium and they guarantee safety. And one other advantage of this is that we can use standard solvers to compute these invariances. But it also has some disadvantage that is obvious in the figures. It is symmetric in the space of activation functions. And this causes that if the equilibrium is close to the boundary, these regions become small and they cannot really capture the maximal invariances. It requires solving an STP, which is annoying, and these motivated us to improve this approach. So we came up with a very simpler architecture with a few more analysis. So we chose just one layer neural network. Again, this can have a multi-layer, multi-hidden layer here too. So we came up with a one-layer neural network. It doesn't need the equilibrium. It doesn't have to be positive definite. And based on the established result in reproducing Taylor-Hilbert space, this representation could be a universal approximator. We changed this definition a little bit. We defined V as being the linear combination of activations inside the constraint set, and we made it equal to G of X, where G described the constraint set. So we had this admissibility condition that if V is greater than or equal to G outside the constraint set, the admissibility condition is satisfied. You can see in the figure that O is a subset of X whenever V is equal to G outside the constraints. And then we try to learn theta for the region inside the constraints. Using this optimization problem, and where again we minimize V to maximize its unity sublevel, and we learn we enforce this invariance condition. Again, if you don't have the model, and also that is a semi-infinite linear program, we use data-driven approach where the constraint of the optimization is enforced on data samples. And of course, we're going to have an issue here because life is not so easy. So the issue is here is that the first norm of the parameters appears in the buffer that we add to provide guarantees. And this causes the LP not to be an LP anymore. So we came up with a trick that we decomposed the parameters into the positive space and negative space. And this allowed us to express the first norm as some linear relation of the parameters, solve an optimization problem, create theta, stick it in V, and create the invariance. And this tells us if the system is Lipschitz continuous, the activation functions are Lipschitz continuous, this constraint set is compact, then the completed set is constraint admissible control invariant, positive invariant. Now another question is that how can we choose these activation functions? In our numerical results, we mostly use radial basis functions. And from established results in reproducing kernel-Hilbert space, we know that these basis functions, under some assumptions that the domain that we are learning the function for is compact. The kernel matrix is positive definite, and there are some centers for these basis functions. The density of centers should be small. It should be large enough. The distance between the centers should be small enough, and the centers should be also distinct because of this positive definiteness. So we can see a 1D example in the bottom. We have 5 basis functions, and we can adjust their height to approximate a continuous function. On the right, you can see a 2D example how we can approximate the function using basis functions. For numerical results, we used 4 different basis functions: inverse exponential, continuous piecewise affine, inverse quadratic, and inverse spline. The 2 on the top I came up with. They have better performance computationally because they are 0. They have value around the center, but they are 0 everywhere else. This will introduce sparsity to the linear program that you're solving and makes the computation faster. Here are some comparison of these 4 basis functions. As you can see, all work well in inner approximating the maximal positive grades. Now let's talk about the consistency of approximation. Consistency of approximation means that in function approximation, it means that if I have infinite data, does my approximation converge to the actual function? Here in our problem, we do not have an actual function v that we are approximating. There might be infinite function v that describes an invariant set. But we kind of redefine the consistency, the definition of consistency for our problem as if we increase the sample data, does our computed set converge to the maximal invariant set? And as you can see, we did some empirical verification. As we increase the data, as you can see, this converges to maximal invariant set. Here is some other results, numerical results. We did for that pyramid, the continuous piecewise affine activation function, and we computed the false negative ratio, which is the ratio of labeling a state as unsafe, but it is actually safe. And we do not have a false positive ratio, false positive error, because we gave guarantee that our computed sets are safe, are inside the max PX set. So in this table, you can see as we increase the data and we increase the number of centers, the density of centers increases, density of data increases, and the error converges to 0. This is the maximum computational capacity that we have. Now, what type of guarantee we can give using our method? We already talked about deterministic guarantee, that by adding that buffer to the inequality of the optimization problem can be provided. But we also investigated probabilistic guarantees that has some benefits. So we saw that using that buffer for Lipschitz continuous systems, for Lipschitz continuous activations, and with very high data density, we saw that we can give deterministic guarantees, but these are some disadvantage to this method. But its advantage is that it will give us guarantees constraint satisfaction. And there's also another disadvantage that adding the buffer may cause infeasibility. To prevent this, we need to increase the data density. And it's good for the soft landing problem where we don't want to violate the constraints. So we also investigated probabilistic guarantees, which uses random data to compute invariant sets. Doing so, we will need less data, but in exchange, we only get probabilistic guarantees instead of deterministic. So the advantages of this method is that it doesn't need the buffer, and deterministic guarantees, giving deterministic guarantees for chaotic system is just impossible for some of them, because their invariant set sometimes is a fractal, meaning that its boundary is has infinite details. There is no smooth boundary to be computed. But the disadvantage, of course, is that these guarantees are improbable systems. Here's an example of Julia map, which is a chaotic system. This boundary has a fractal behavior, and we have computed a inner approximation of the invariant set with probabilistic guarantees. Well, what do we mean probabilistic invariance? What do we mean by that? So let's define some concepts. Let's define accuracy as if we have a set and we draw a random sample, and we look at and see if this sample admits to the invariance conditions. We look at this probability, and the bound on this probability would be defined the accuracy. We define confidence. We need another variable because we have another layer of probability. Where does it come from? It's because the set itself is a random variable because it is computed using random data set. So the set is a random variable, and verifying the set using a random data is added another level of probability. So we define confidence as the computed set being 1 minus epsilon accurate. Yeah, as the probability of the computed set is being 1 minus alpha accurate. So we came up with a theorem that if the data is drawn randomly and that optimization problem is solved without the buffer, then the set O is 1 minus alpha accurate with confidence 1 minus beta. The set O is positive, constraint admissible positive invariant with accuracy 1 minus alpha and confidence 1 minus beta. Here's another example. This is a Lorentz attractor. It resembles the butterfly effect where slight changes in the initial condition causes drastic change in the trajectory. And it's a benchmark for climate estimation, climate forecasting algorithms, and it has a fractal invariance set. And you can see a trajectory that starts outside our computed invariance set, it violates the constraints. But the trajectories that are inside stay the same. Now, how can we use these algorithms that we developed to compute controlled invariant sets and apply stage control? So if the controller is just a state feedback, we create a closed loop system, treat it as an autonomous system and compute a positive invariance. But if the controller has some dynamics to it, then we create this augmented system, and we compute a positive invariance set for this system, which gives us a control invariance set for the primary system. also have another approach if we have a collection of the controllers. If you have a collection of controllers, we create a closed loop system using each controller, draw samples, compute invariance set for each of the controller in the loop, and then take the union of these computed invariance sets, and this will give us a control invariance. As you can see in the figure on the top right, for each value of u, we computed an invariance set. And if we map this onto the face plane, it will give us a control invariance. Now, can we develop another algorithm to compute maximal invariances? Because those methods that use a controller, the shape of the computed control invariance set highly depends on the controller. And the controller may not take us to some places in the state space. So if you have a data set that contains the state, and for each state we have several inputs, and this will give us several state successors for every state, and then we compute an initial invariance set when with the zero control input. This zero kind of means that if we have a stabilizing controller, we apply that to the system, create an initial positive invariance set, and then iteratively solve this optimization. This optimization, again, it tries to minimize this function v to maximize the invariant its sublevel. The first constraint here tells us if a state under some input maps inside the initial invariance set, then it should be considered on the next iteration as safe. The second constraint tells us if we have already classified a state as safe, we don't want to lose it in the next iteration. We should be classified as safe. And as you can see on the right, the initial invariance set is the blue, and we iteratively solve this problem, and as you can see in 8 iteration, it converges to the maximum controlled invariance set. Now, how can we use these approaches to create switch controllers? The switch controller has this structure. There is a supervisor that switches between some existing stabilizing controllers, and we want to minimize some cost function subject to that the current state that we have measured is inside one of these invariant sets with respect to the controller. So we applied this to soft landing problem. The soft landing problem is hard to solve because the equilibrium is on the boundary. And if we try to compute a Lyapunov function, it might be infeasible because it's symmetric if we want to create an invariance of using a Lyapunov function. Because it's symmetric and it cannot have volume around the equilibrium. But using the barrier function, we could compute an invariance set for the system. We used some state trajectories of a second order underdamped system. We chose a second order underdamped system because we wanted to see constraint violation for some initial conditions. And we designed an LQR controller to take the system to the equilibrium, and we applied some. The LQR controller makes the system underdamped, but adding an actuator saturation, again for some states of the system behaves in an under them. So we computed a positive invariant set for this system. As you can see, when you start inside the positive invariant set, it converges to the origin. If you start outside of it, it might violate the constraints. And this informs us that we need a secondary controller to be more aggressive. So we designed a bang-bang controller. The bang-bang controller is not doesn't have a positive invariant set because whenever we start, it violates the constraint. But since we have only two controllers now, we can just switch between them. Whenever we are outside the positive invariant set, we use the bang-bang controller, and the bang-bang controller tries to drag us inside the positive invariant set, and once we enter the positive invariant set, we switch to the primary controller and converge to the origin. Here are some time plots. You can see without the with the only the primary controller, the system violates the constraints, but applying the switch bang-bang controller regulates the trajectory safely to the origin. Another example that we worked on is lane keeping. We use the bicycle model with constant velocity. It's a second order nonlinear system. And then we designed a switch controller using our data-driven invariant set. The states of the system are lateral position and heading angle. We defined a collection of controllers by creating the command, which is the desired lateral position of the system. And we created a collection of controllers. And then we computed an invariant set for every controller in the loop. For example, on the right, you can see the invariant sets, the boundary of the data-driven invariant set in green line. And then we couldn't compute the maximal invariant set using standard methods because this is a nonlinear system. There's no standard method for that. So instead, we approximated the maximal invariant set by initiating the system from every those green signals. Initiated the system for a long trajectory and just observe that does it violate the constraints or not. This method doesn't give us guarantee, and it needs a lot of simulations for every state. So it's not a good method. I don't recommend it. But it just gives us an approximation of the max invariance. Then we created a command governor for the system that minimizes the adjustment on the desired reference such that safety is also guaranteed. Here are some results. The red trajectory is the desired trajectory, the command coming from the user. The green here is the trajectory using our data-driven switch control approach. And the yellow here is using a nearest neighbor. Well, it uses that approximated maximal positive invariant set using that heuristic method that we used. And if it looks at the current state and picks the nearest neighbor, that if the nearest neighbor was classified as green or safe, it applies the input. And that heuristic approach doesn't give guarantees, and in simulation we saw that it violates the constraints a few times. And that's how we can do data-driven constraint control. Thank you so much for listening. much overtime I was.
Almost an hour.
I mean, that was, I think, perfect timing. We started 10 minutes late, so that was right at 45 minutes. Exactly. Are there any questions?
Yeah, I have two questions, I guess. The first one is on the Bang Bang controller for the soft landing problem. Specifically, when you're starting outside of the control invariant set, is there some condition of like how far away you can be outside of the control invariant set where it'll still work? Or like, I'm assuming if you're too far away, it won't work.
Yeah, if you're too far away, it won't work. So, for example, this is a soft landing problem, right? You are riding your car, and you are going with some speed toward the wall. All you can do is just brake, right? So you might hit the wall or you might not. All you should do is just to brake, and that's what it does until you reach to a safe distance with safe velocity where you can stop braking and just continue. For example, if you reach a red light.
Yeah. Cool. And then the last question for me is just for the deterministic guarantees, that buffer. In practice, is there a way to select that buffer, or is it kind of you have to try some buffers that are feasible or that work to?
No, we computed the buffer. You look at if you have an upper bound on the Lipschitz constant of the system. There are some methods to compute an upper bound on the Lipschitz constant of the system, and these activation functions, you define them. You have their Lipschitz constant, and you also can have more data with more density, right? And I showed that buffer relates to these three parameters, and you can create that buffer and just stick it in the optimization problem and solve the optimization problem. Thank you. Really good.
Hey, Ali, a really solid presentation. I wanted to ask about some of your experience with the Maximal PI set. The reason why I ask is Rihanna and I had a paper that we were looking at talking about Kuppen operators, and in that framework, it enables you to kind of find more efficient ways to control the system. And I was curious if your Max PI set can give you some insights on the magnitude of your control. Like, can you find, does it require, and correct me if I'm phrasing this question correctly.
Can you rephrase it? Yeah.
I guess like how does it affect the control that you need for I believe a CAPI set? Like, would you need less control, more? Is that
okay?
something you
Yeah.
can say?
Yeah. So those inputs that we apply for each state, it's inspired by reinforcement learning, and we apply inputs on a limited interval. So if we assume that if we have infinite authority over the input, we can just apply infinite, like u equal to infinity to the system and just take the system to any state you want, under some assumptions of nonlinear systems. But if the system has limited authority, we create that interval that the input can be applied, and then apply some of those inputs. And then, compute the successor state, and that gives us the maximum control degrees. Any questions from that, please?
If you took your controller for this, and you took the data that you got for this, because now you have a nonlinear controller,
Yeah.
what would your PI set look like?
So the controller, I tried to compute that.
Okay.
I tried to compute that. I couldn't compute that. I think it's because of the Bang Bang controller is not is very crazy around the equilibrium. It jumps a lot, so I think it's not, the system is not just continuous anymore. It acts very crazily around the equilibrium.
So Bang Bang, but if you did Bang Bang LQR, right? So you have
Yes.
one
If
plus
I-
one minus one.
Yes. Bang LQR is, acts smoothly if the trajectory enters the positive
Okay.
axis. If it doesn't, it will go that way and it becomes crazy around equilibrium.
Okay.
Yeah.
One thing, just to give you an opportunity to maybe show off to the committee, slide 20. Can we go to that? So it maybe got lost on the audience, the importance of this geometric condition. It might have been after this slide. You had the slide on the geometric condition for invariance. Yeah, this one. Can you talk about how you use that in your theorems?
Yeah, of course. I use this for the computing the maximal control invariance.